Good morning, everybody. Can you believe it? It is already Thursday, and oh my goodness, it is already third period. I hope you guys are having a great day. You get to have virtual me to here today, and so hopefully you maybe even enjoy it more. What I'd like you to do is I want to start by kind of going over the homework. As I look at it, I really think that it was pretty simple. But go ahead and make sure your homework is out. Don't hand it in just yet. I want to go through it step by step and make sure you're good. And so, all of it was just about, kind of continuing these patterns and talking about what the patterns could have been. And then we did talk about that there was 16 and 17 near the bottom of the sheet. We're going to have at least a little bit more work, so I definitely want to talk about those. And then that 18 through 20, some people may have done those for extra credit. I want to take a quick look at those and not spend too much time, but just help you kind of see why I thought those were so interesting. Okay, so without any further ado, let's get going, okay? So you can just kind of go over your own homework right now and make sure you have the answers that you should have. Okay, so on this first one, we're going 17, 23, 29, 35, 41. Hopefully you saw that the pattern, they are simply adding 6 every time. And so if I was to continue this pattern, it would be 47 and 53 and 59 and 65 and so on and so on and so on. Okay, pretty simple. All right, the next one says 1.01, 1.001, 1.0001. All right, now this one is less mathematical. There is a formula I could set up, but really I think it just, if you showed this to anybody, they would just say, well, you're kind of putting in another zero there. I wouldn't use the words you're adding a zero, because to add zero is to add nothing. But I could say, less mathematically, you're inserting a zero, and I think that would be okay. And so, I could say, well, I'm inserting a zero behind the decimal. Sorry for the sloppy writing there. Inserting a zero behind the decimal. Okay, and so the next one would be 1.00001, and after that it would be 1.0000001, and again and so on. You're just inserting an additional zero behind the decimal. Okay, this next one, it says 12, 14, 18, 24, 32. Now I'm curious if anybody saw this one. It probably took a little bit more work, because 12 to 14, we added 2. 14 to 18, we add 4. 18 to 24, we add 6. And 24 to 32, we add 8. So the pattern isn't so much in these numbers as it is in these numbers. And what we see is we are increasing every term by the next even integer. Okay, so therefore, I'm going to go plus 10, and then there's going to be a plus 12, and then a plus 14. And so, you could say increasing by the even integers. That would be how this is growing. It is increasing by even integers. That would be a good description. So 32 plus 10 is 42. 42 plus 12 is 54. 54 plus 14 is 68. And it would keep going on and on and on. Okay, the next one. Now, this next one, you might say, well, this one's not very mathematical either, but it's actually very mathematical. It's really simple. This one, all I'm doing is I'm multiplying by a -2. See, 2 times -2 would give me that -4. -4 times -2 would be a positive, and it would be positive 8. And then times -2 is -16, times -2 is positive 32. So the next one is going to be, times -2 would give me -64. Multiply by -2 after that, it's going to be a positive. It's going to be a positive 128. Times -2 is going to be -256. And then a positive 512. Pretty simple. All right. Now, this next one, probably, I think 5 and 6 are probably the most challenging. But hopefully, again, after looking at number 3, you might see number 5 in a different light right now. And you go, okay, to get from 1 to 2, I add 1. To get from 2 to 4, I add 2. 4 to 7, I add 3, and 7 to 11, I add 4, and hopefully you see it by now. Look at what's happening here. In what I'm adding, that's just increasing by 1 every time. So you could say each term is increasing, I guess would be how to write it, increasing by the counting numbers. Okay, really that's all it's doing. It's increasing by the counting numbers. So the next one would have to go up by 6. So that would make this 22. Then I've got to go up by 7, and making this 29. Go up by 8, 37. Go up by 9, 46. Go up by 10, 56, and so on. So it's pretty simple. All right, number 6 is probably the most challenging. Hopefully you kind of looked at it the same way as we've looked at these last two, and you've looked at what's going on there. But this one, it wasn't adding, but it's subtracting. And what's funny is you look at, it is adding, but the amount that you're adding is going down. You aren't subtracting. Sorry, I misspoke. So 32 to 48, you're adding 16. 48 to 56, you're adding 8. 56 to 60, you're adding 4. 60 to 62, you're adding 2. And 62 to 63, you're adding 1. So then my question would be, well, what's happening with these numbers? And the answer is, maybe you want to say the amount increasing. Ooh, that was interesting. I don't know what is going on with the little circle there, but we'll get rid of it. Okay, so the amount increasing is being what? It's being divided by 2. The amount increasing is being divided by 2. Every time we go up, the next time we go up by half as much. First we went up by 16, and then by 8, and then 4, and then 2, and then 1. So what are we going to increase by now? Well, half of 1. So we're going to go up by half, or 63.5. Then we go, well, now I'm going to go up by half of that. And so half of that would be 0.25. So it would be at 63.75. And then we'd go up by half of that. And half of 0.25 is 0.125. And so now we would be up to 63.875. And then half of that is 0.0625. Ugh, this is starting to get crazy. And so you see where I'm going. Okay, that's enough terms if you've got that much. All right, now we're going to look at 7 through 12. But 7 through 12, we talked about those yesterday. They give you an opportunity to be creative. So there's really no right and wrong as long as you showed enough to continue the pattern. If all you did was write one number, one letter after what was shown, well, then you didn't continue the pattern. You just picked a number. I need you to write enough that you could see what was going on. But I can't talk about all the possibilities. If I was there today, I would ask, a handful of different people what you got and what you did for this one, what you did for that one. But without me being there, I just have to say, well, I hope that you continue those patterns well. All right, so what we're going to do is we're going to move down to 13, 14, and 15, okay? And so 13, we've got to say what is going on in this pattern. And it says draw the next figure in each sequence. Well, as I look at this, the first thing I have is I have a 3-sided figure, and then a 4-sided figure, and then a 5-sided figure. So I feel pretty confident at this point that my next one should be a 6-sided figure, okay? Now, another way of looking at it is you can say, well, wait a minute. I started with a triangle, and still that triangle was here, and they added another triangle. And then to that rectangle, they added another triangle. So that's another way of looking at it. So there's really 2 right answers. You could say that it looked like, maybe I should add a triangle to the top, and it would look like this. And I'm okay with that. Or you could say, well, no, I just, added another side and made it a 6-sided figure. So either way, that's really what it should be, is you should have a 6-sided figure right now. I don't really care exactly what it looks like, but if nothing else, you should have seen that the first one was 3-sided, second was 4-sided, third one was 5-sided, and now we should be up to a 6-sided figure. Okay, on this next one right here, you see we have a circle that's cut in half, and then a circle that's cut in half and then cut in half. And then this is where it gets interesting, because they only added 1 line to get from the first to the second, but then to get from the second to the third, they added 2 lines. So what they did is they cut every section in half, not just one set of the sections. And so really at this point, if you think about this one, what we'd have to do is we'd have to say, well, we're going to cut a lot more in half. We would have to cut this one in half, and this one in half, and this one in half, and this one in half. Okay? And it would actually look like that. Now, maybe I should have did that all in black so it doesn't pop in 2 different colors. But basically, one of the ways of looking at it is you could say, well, this one has 2 parts, this one has 4 parts, this one has 8 parts. So therefore, as that's doubling, this one should have 16 parts. So hopefully you're able to count all 16 of your parts. Okay. Number 15 is probably the problem that most everybody gets wrong. Okay. Not everybody gets it wrong, but a lot of people get it wrong. It really is very similar to number 6. How much it's increasing by is getting cut in half. But it's hard to tell that when there's only so few parts of the sequence. But we started with this idea of 90. Maybe we can assume that before that it was actually a 0-degree angle. And so it increased by 90. And then from 90 it went up to 135. So it increased by 45. And then from 135 it went to 157.5, which means it increased by 22.5. And look at these three values. They're getting cut in half every time. So what's the next one? Well, the increase would be by 11.25. Now, almost everybody just writes a straight line and says it's 180, but that's not the case. For this one, actually what it should be, and let's see if I can try to draw it. I don't know if it's going to go real well, but we'll pretend, right? Oh, that didn't go so well. Let's try that again. Man, having a problem here. Okay, let's get rid of all this. Try it one more time. Okay. Booyah. There we go. Okay. And so at this point, what I can do is I can take this value of 157.5 and add to it 11.25. And what would I get? I would get 168.75 degrees. So that's what you should have. Very few people ever get that one right. I'm sure a couple of you did, but if you did, you're a rock star. If you didn't, don't worry. Almost nobody does. Okay, now let's talk about 16 and 17. 16 says, how many handshakes occur? Okay, now if you don't know how to do this one, or if you didn't figure it out, man, make this easy on yourself. How many handshakes occur? Well, all you got to do is think about, there's 7 people there. And so we'll say we had a guy named Al and a guy named Beauregard, and how about Charlie and David? How about Edward? So what is that? That gives us 5. And then Frank walks into the room, and sure enough, good old George. And so look at that, 1, 2, 3, 4, 5, 6, 7. And all you have to do is kind of set this up, and you can see. Well, Al's got to shake Bob's hand, and sure enough, then he's got to shake Charlie's hand, and what was it, David's hand? And Edward, and not Bob, but Beauregard. Man, I can't believe I did that wrong. And Frank and George. Okay, now when I get to Beauregard, or Beau, he's already shaken Al's hand. So he doesn't have to go back. He can't shake his own hand. So the first person he moves on to is Chuck, or Charles. And then he goes over to David, and then to Edward, and then to Frank, and then to George. Now, in the same way, when you get to Charlie, he has already shaken Al's hand, already shaken Beau's hand. He can't shake his own hand, so the first guy he moves on to is David. And then Edward, and then Frank, and then George. Okay? Now, a lot of people, when they're doing this one, they think, oh, it must be, 7 people, so it's 7 squared, so it must be 49, or something like that. But that's not the case. We can see that there's no way there's going to be 49 handshakes. Maybe you don't see that yet. Okay, let's talk about David. David's already shaken Al, Beau, and Charlie's hand. And so now David can't shake his own. He moves on to Edward, and then Frank, and then George. You guys see the pattern right now. Eddie already shook everybody's hand, so he moves on to Frank, and then George. And at this point, Frank, he can only shake George's hand because he's already shaken everyone else's hand. It shows up right there. And right now, George, he's already shaken every single person's hand at this point, so he can't shake his own, so we're done. And so look at what you have. Here in this first column, you have 6, and then the next column, you have 5, and then after that, you have 4, 3, 2, and 1. And if we add those up, 6 and 5 is 11, 4 more is 15, 3 more than that is 18, 2 more is 20, and plus 1 more is 21. So we weren't anywhere near that prediction of 49, but that's what almost everybody says. Oh, I bet it's 7 squared, but it's not. That would be if every single person shook everybody's hand a couple times over and shook their own hand. And so that doesn't work, okay? So the total is 21. And so the hard thing is you go, man, where does the number 21 come from in relationship to the number 7? Because on this next one, it says, using inductive reasoning, write a formula. Well, I hope if nothing else, you see this, inductive reasoning. And we said last time we were together that inductive reasoning meant that you were seeing a pattern. And right here, there is no pattern because we did it one time. You can't have a pattern with one time. So what you've got to do is you've got to say, well, let's see how many handshakes would happen if there were a different number of people in the room. That's the only way you can use inductive reasoning. Okay? So to do this problem right, you had to create a pattern. And so I'm going to do that right now. Okay? Let's say there's one person in the room. Well, one person in the room, they can't shake their own hand, so there would be 0 handshakes. Okay? 2 people in the room. If there were 2 people in the room, they would walk up to each other, shake hands, and they're done. There's 1 handshake. Okay, now let's think about 3 people in the room. Now I might have to write off to the side to make sure we got this, but 3 people would be like A, B, and C. Well, A would shake B's hand. Well, hang on, let me do that different. A would shake B's hand, A would shake C's hand, and then B would move on to C, and then we're done. So 3 people would be 3 handshakes. If I had 4 people, like A, B, C, and D, A would shake B, and then C, and then D. B would move on to C, and then D, and then C would only have D left. And that's 3, 2, 1. That's a total of 6. So 4 people. You see this is already increasing pretty quickly, but with 4 people, I would have 6 handshakes. Let's try it with 5. Okay, with 5 people. Whoa! With 5 people, I would have A, B, C, D, and E. And so again, yikes, I'm scooting this paper down real well. Okay, with 5 people, I would have A shakes B, A shakes C, A shakes D, and A shakes E. B would have to move on to C, D, and then E. C, at that point, moves on to D, and then to E. And lastly, D only has E to shake. And so now that's 4, 3, 2, 1. And so that's 10 people, okay? And we can keep going on, but hopefully maybe we even notice a pattern here. Look, it increased, as we look at these, we said, well, this first one, it increased by 1, it increased by 2, it increased by 3, it increased by 4, and that makes sense, okay? Now here's the problem. While this is a pattern, that's not helpful to come up with a formula, because the formula would have to be based on that we don't know the previous number. So it's not that we can take 10 and then add 5 to it and know that with 6 people, let's go back to blue. With 6 people, I'm going to end up with 15. And therefore, with 7 people, we know we're going to end up with 21. And so we had our plus 5, we had our plus 6, and that's great. But what if I said, well, now there's 42 people in the room? I don't want to have to say, well, plus 7 and plus 8 and plus 9 and plus 10, all the way up to 42. That'd be a nightmare. Okay, so I can't do it this way. I've got to look and see what pattern do I have. And when I say that, let's take a look at these numbers. Okay, kind of put them in like a little XY table or something. And this is number of people, and this is number of handshakes. So with 1 person, you get 0. 2 people, you get 1. 3 people, you get 3. 4 people, you get 6. And 5 people, we got 10. And 6 people, we got 15, and 7 people, we got 21. So the question is, do you see a relationship that will take you from this number to that number? And it's the same relationship that would say take you from this number to that number. And I don't know if anybody found this or not, but here's what I noticed. And this is kind of crazy. But look what happens when I multiply some given number by 1 less than that number. So I've got 4 people in the room. 4 times 3 is 12. And when I cut that in half, I get 6. And notice that kind of continues, okay? If I say I have 7 people in the room, 7 times 6 is 42. If I cut that in half, I get 21. So the pattern works again. If I have 5 people in the room, I multiply that by 4. 5 times 4 is 20. I cut that in half and I get 10. And so there's a formula that will work, okay? I could take however many people are in the room, we'll call it n. I would have to multiply it by 1 less, or n minus 1, and then take that answer and divide it by 2. So the number of handshakes is always going to be equal to however many people are in the room times 1 less than that divided by 2. And so in that, what that would mean is, that would mean that if I did have 42 people in the room, I could say, well, 42 times 41 divided by 2. 42 times 41 is 1,722. Divide that by 2, 861. If you had 42 people in the room, there would be 861 handshakes. Now, that's way better than us working through it step by step just to get there and adding and adding and adding. Oh, that would have taken a while to get to 861. So that's why we want to use inductive reasoning to create a formula. All right. Now, if at this point you feel like you have the extra credit done, I would like you to turn in your paper. If you, well, actually, at this point, let's make it easy. Let's have everybody turn in the paper, okay? Everybody go ahead and turn in their homework. I'll give you just a minute to do that. We can pause the video right here, and then I'm going to talk about 18, 19, and 20 briefly. So go ahead and pause it, and then we'll take a look at that. All right. Hopefully you got that taken care of. So now let's take a look at how the rest of this goes. Now, obviously, number 18 is really simple. It says, hey, what's the 9th term of the Fibonacci sequence? Remember, in the Fibonacci sequence, we always add the previous number. So we get 1, and the previous number would have been nothing. So 1 plus nothing is 1. 1 and 1 is 2, and 1 and 2 is 3, and 2 and 3 is 5, and 3 and 5 is 8, and 5 and 8 is 13. And what did it? It went up to this point. So that's the 1, 2, 3, 4, 5, 6, 7th. Okay, first 7 terms. Well, 8 and 13 is 21, so that's the 8th term, and 13 and 21 is 34. So that's the 9th term. Like I said, number 18 was easy. But then we get into this idea of what about, let me get rid of that. What about this idea of successive ratios? If there's any part of this whole page that's unbelievably interesting, it's this. It's this idea of successive ratios. You might say, well, I don't know what that means. And I'm not going to take too much time to talk about it because I'm not there in person, so I might lose you a bunch of you, but I don't mean to. Okay, but successive ratios. Well, let me write a bunch of this real quick. Let's see. We'll take this group right here. This is the first, I don't know, bunch of terms of the Fibonacci sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The first 15 of the Fibonacci sequence. We're going to take that and we're going to look at that. So successive ratios, what am I saying? Well, I could write that one of two ways. I could either say that's, I'm going to put one term over the next term, or I'm going to put one term under the next term. And that would be how I'd come up with successive ratios. In the book, it says, look at successive ratios, on the page, look at successive ratios of one term to the next. And so, we kind of look at this. And so I could say, well, we're looking at 1 to 1, and then 1 to 2, and then 2 to 3, and 3 to 5, 5 to 8, 8 to 13, 13 to 21, 21 to 34. And now this may look really stupid, but remember at the beginning of this problem it said use a calculator. And so then I'm just going to keep writing these so I kind of save a little bit of time. 34 to 55, 55 to 89, 89 to 144, 144 to 233, 233, oof, that's an ugly 3, to 377. Sorry, I'm trying to write small, as I write smaller and smaller, my writing gets sloppier and sloppier. Okay, so what I want to do, that is probably going to be plenty for us to do. But if you had a calculator right now, and I don't need you to have a calculator right now, I'll do the number crunching for us. 1 divided by 1 is 1. But 1 divided by 2 is 0.5. 2 divided by 3 is 0.6666 forever. And then 3 divided by 5 is 0.6. And then 5 divided by 8 is 0.625. And 8 divided by 13, well, it's a pretty long and ugly decimal, but I'm going to give you the first few of it. It's 0.6154. We'll round up a little bit. And then 13 divided by 21 becomes 0.6190. And I don't know if you guys see what's happening, but we started with 1. went all the way down to 0.5, and then went all the way up to 0.666, and then down to 0.6, and then up to 0.625, down to 0.6154. And so the numbers they keep getting smaller, and then bigger, and then smaller, and then bigger, and then smaller, and then bigger. But notice the distance between the smaller and bigger is getting smaller itself. It's almost like it's kind of refining closer and closer to 1 point. Okay, so the last one I did was 13 over 21. I'm going to keep going and say 21 divided by 34. And 21 divided by 34 is going to be 0.6176. And then 34 divided by 55. And I get 0.6181818 forever and ever. Okay? And where am I at? Now I'd go 55 divided by 89. And I get 0.61798. So again, it got a little smaller, and then we assume then that it's gonna get a little bit bigger. So now I'm gonna do 89 divided by 144, and I get 0.61806. And then we go 144 divided by 233, and it goes 0.61803. So you see that we're really splitting hairs at this point. It's getting tighter and tighter. And so 233 divided by 377 is now 0.61804. And so it is now getting so close, it's barely changing. And so you go, man, okay, but what in the world is it doing? Excuse me. And you can see it's getting closer and closer to some number, 0.6180 something, that it's refining, and it's called converging on a value. And what it's doing is it's converging on what's called the golden ratio. Okay? Now all you gotta do is Google the golden ratio, and you'll see a billion of really cool images of what that is. It's a ratio that's been around for a few thousand years. It's been around forever, but it got discovered a couple thousand years ago. And what it is it's a ratio of that if you have a rectangle, you can cut off a square and be left with a rectangle that has the exact same proportions as the original rectangle. So that way, when you cut off a square, you're left with a rectangle that, again, has the exact same proportions as the original rectangle. Now, mine doesn't, because I can't naturally draw the golden ratio. But if you look it up, what it is it's a way that we see that it's called like the perfect image or the perfect ratio. The human body itself is broken up into several golden ratios. It's all over the place. There's the way that our face is structured, the height of our eyes being in relationship to the top of our head and the bottom of our chin is a golden ratio. Everything about our bodies, everything about so much in nature, even how people now do architecture, they do it by the golden ratio. And not just now, but the Parthenon in Greece, if you know what that is, it's that when you hear about Greece and you picture Greece and you see that big temple with those huge marble pillars, that's the Parthenon. The Parthenon was all designed around the golden ratio. And so this is incredible that something like the Fibonacci sequence, which all we had to do was add one term after another, that when you divide these, you get this beautiful thing called the golden ratio. If you got some time, look it up. Maybe when I get back, we'll take a quick look at some of the things that the golden ratio involves. It's incredible. All right, and lastly, let's talk about number 20. Number 20 is kind of a dud of a problem after number 19. Number 20 just says, hey, find the differences of successive terms. And I don't know if anybody tried this, but it's actually pretty obvious. You go, well, what's 1 minus 1? Well, that's 0. Well, what's 2 minus 1? That's 1. 3 minus 2 is 1. 5 minus 3, 2. 8 minus 5, 3. 13 minus 8, 5. 21 minus 13 is 8. And 34 minus 21 is 13. And 55 minus 34 is 21. 89 minus 55, well, that's 34. Hopefully at this point you notice, look what I have here, adding things. And so if we subtract them, of course we're gonna get the Fibonacci sequence back. So I feel like this was kind of a dud of problems, but that's all right, okay? Anyway, what I'd like you to do right now is we are done looking at our homework. And so at this point, we can be done. We're going to start another video talking about what we get to do today. I hope you guys are having a great morning so far, and we can start that next video.